Hello everyone. I would like to start off this lesson by talking about something called the vertical line test. All right, this is just a quick test that you can use when you are looking at a graph of a function, whether the function is defined by a graph or whether it's the graph of an expression that's a function. The vertical line test is a quick and simple way to determine whether this graph you're looking at is in fact a function. And all it says is that if you take a vertical line and you intersect this graph, you should only be able to intersect it at one point and only one point anywhere on the graph. All right, so if I take all these vertical lines and put them in these random spots, you can see that these vertical lines are only intersecting this y equals x squared function at these singular points right here, which indeed makes y equals x squared a function. Yes, it's a function. Now, if I look at this function here, or rather this graph over here, and we want to know whether this is a function, yes or no, if I put a vertical line over here, once again, I'm only seeing intersecting once, but if I go somewhere else, I might see it intersect more than once, maybe 2 or 3 times or something. And this means that no, this graph here that we are looking at is in fact not a function. So this is a quick test that you can do, again, whether this graph is defined by an actual expression or whether it's just a graph that's drawn. Now, there is something else. Again, the vertical line test determines whether this is a function or not. But there is also a horizontal line test, which determines whether this function is called one-to-one. And one-to-one essentially means that that each input has a unique output. Right? So if we look back at y equals x squared, once again, we are seeing this thing pass the vertical line test. So yes, it's a function, but we are seeing the horizontal line test fail because a horizontal line drawn through this graph intersects the function twice. All right, so by the same token, a vertical line test tests. The horizontal line test is the same if a horizontal line passes through the graph in more than one point, then the graph, it's still a function based on the vertical line test, but it's not a one-to-one function, right? So y equals x squared is in fact not a one-to-one function. A very classic looking one-to-one function is y equals x to the third power, right? You can see one point of intersection at these vertical lines here. And we're assuming that this, again, our knowledge of how the graph behaves can let us determine, because it's going on forever in either direction, right? It's impossible to check every single point at every single value from negative infinity to positive infinity. But our knowledge of how these graphs behave can help us determine that this is a function, yes. And it also can help us determine that this is indeed a one-to-one function. Because again, we know how this graph behaves even beyond the picture that we are actually seeing. So that is the vertical and horizontal line test. Again, a quick thing. One thing is that if we take a look, let's go back to y equals x squared. I'll draw this in black right here. Right, y equals x squared is a parabola that goes through the origin, and again passes I'll draw it once again, passes the vertical line test, again in various places, in any place, but does not pass the horizontal line test. So what some computers and functions do, right, what machines and stuff like that do, if they need to use y equals x squared as a one-to-one function, right, something that can kind of like a hack is that they can restrict the x values from 0 to infinity, effectively erasing 1/2 of this graph. Effectively erasing 1/2 of this graph so that it does become 1-to-1. Because now if we're only looking at x values that are positive, basically the right half of this graph, now this is a 1-to-1 function. So an inverse of a function. In order for an inverse of a function to exist, the function itself has to be a 1-to-1 function. Excuse me. And again, in order for a function to be 1-to-1, it has to pass both the vertical and horizontal line tests, and that basically indicates that each input yields a unique output. Right? Remember we talked about how functions, the cardinal rule of a function is that in two different inputs can give you the same output. It's possible to do that, especially in a lot of the machines that we use in daily life. We're able to do the same, make a machine or a phone or a game do the same thing by pressing two different buttons. But now for a function to be 1-to-1, that means you can only do a certain thing by doing one of these things, right? Pressing one of these buttons. So in a sense, a lot of older games that you play on controllers are not 1-to-1. Keyboard is not 1-to-1 because there are two shift buttons, those kind of things. But a lot of games are. These days, a game that utilizes every single button to do something unique, it is a 1-to-1 function. So, an example of a function is y equals x to the 4th power, but this is an example of a function that is not 1-to-1. Y equals 2x minus 7 is one of the many examples of a 1-to-1 function. Right? Something like this over here is basically a 1-to-1 function, but something like this is not. Straight lines are 1-to-1 functions. Straight diagonal lines that we see, something like 2x minus 7 over here, is a straight diagonal line. So, to find an inverse, right, to find the inverse of a function, if it is defined or given to you graphically, all you are doing is swapping the x and y coordinates. Right, so if we are starting with something like a coordinate ordered pair of 2, 3, we can find the inverse to that particular input and output just by swapping 3, 2. 4, -7 becomes an ordered pair of -7, 4. And all of these put together should give you an idea of how the function looks graphically as an inverse. Now, one thing graphically that an inverse does is it reflects. It is a reflection around the line of y equals x, right? And that is what I've drawn here, which is in blue, a function of y equals 2x plus 1, f of x equals 2x plus 1, however you want to say it. And I drew in a dotted line over here in red, that's y equals x. So I'm gonna plot some of these points in green and show some of the inverse points here, right? We have a point over here of 0, 1. I didn't write that down, and I certainly can write that down. Right, and we have another point over here. I'll draw a line. That's an ordered pair of 1, 3. So if we want to plot the points on our inverse line, right, the inverse from 0, 1 would be 1, 0. And then from this point here, 1, 3, that would be 3, 1. And then 5, 2, and then 7, 3. All I'm doing is switching the x and y values for these ordered pairs. And if I go to the other side, this ordered pair is -1, -1. which will swap to be the same thing, and then over here, negative 2, negative 3 is going to become negative 3, negative 2. So what we are seeing here is the inputs and outputs for this function, which will have its own expression as well. Just and we will cover how to find that. So again, 7, 3 for this ordered pair, 5, 2 over here for this ordered pair, over here, 3, 1, and so on and so forth, right? So it is possible to have an inverse kind of plot at the same point as it started with, but overall, all of the points put together are going to create a new line. And you can see that it is indeed a reflection around y equals x. So, moving forward, I want to talk about the notation that you're going to see, right? Because this notation is potentially slightly confusing, at least in the beginning stages. So, I wrote this before. Let's go back. Over here, when I was looking at the ordered pairs, these ordered pairs are from the original function, generally called f of x. And these ordered pairs that I swapped, these are from the inverse function, which is notated by this f negative 1x, right? It looks like f raised to the power of negative 1. Remember, here in algebra, x raised to the power of negative 1 essentially means 1 over x. But the confusing thing is that this looks like it's a exponent raised to the negative 1. In fact, it is not. This is not an exponent. All this is the notation, the shorthand of an inverse function, right? If a function is labeled to be f of x, that means its inverse is going to be labeled as f negative 1 of x. If a function is labeled as g of x, that means the inverse is going to use the same notation, g negative 1 of x. And I'm not going to say g raised to the power of negative 1 or something like that, right? And then in addition to that, this rule of algebra, which means you move the base value down to the bottom or top, depending on where it started, this is not true for inverses, right? So once again, this is not an exponent, which means f negative 1 of x written this way is actually not equal to 1 over f of x. Right? If your function is 8 minus x, the inverse is not going to be 1 over 8 minus x. That is not the same, okay? So, how do we find an inverse algebraically? There's 3 steps to finding an inverse algebraically. First, you set your function equal to y, and that's really just for labeling purposes. The next thing you want to do is swap the x and y locations, right? This is similar to the ordered pairs where we swapped those numbers of x and y. And the next thing algebraically is we solve for y from its new place, right? So let's take a look at a simple function here. F of x equals x minus 12. That makes y equal to x minus 12. And again, this is really just for notation purposes, for moving forward, operating with y instead of f of x. So the next thing we want to do is swap the locations. If y equals x minus 12, that means x is equal to y minus 12, right? We are literally swapping the locations of x and y, just like we did on the ordered pairs. And now we want to solve for y. So y is equal to x plus 12, and this is the inverse of our original function. Right, our original function was x minus 12, and our inverse is equal to x plus 12. And that's it. That's all there is to finding the inverse. But, of course, it can get more complicated as your function gets more complicated. So let's look at this one. G of x equals 10x plus 29. Again, start out by setting y equal to 10x plus 29. And then continue by swapping the locations of x and y. That's 29. So we can solve this by subtracting 29 from both sides, and I'm going to switch it right here. 10y is equal to x minus 29, just because I like the variable I'm solving for to be on the left. We can divide everything by 10, and that makes y equal to x minus 29 over 10. So our original function was called g of x, which means our inverse is called g negative 1 of x. And x minus 29 over 10 is what it is equal to. Box that in, and we are done. Sorry about my throat. H of x equals 18 over 2x plus 9. Means that y is equal to 18 over 2x plus 9. And this is technically a proportion. This is a fractional equation now. Oh, we have not swapped yet. Sorry about that. So let's, I'll put an arrow here. Over here, x is equal to 2y plus 9 on the bottom, 18 on top. Right, so this is x over 1, because any whole number can be put over 1. You put 1 on the bottom of any whole number, any whole value, which makes here a proportion where we can cross multiply. And be careful cross multiplying here, because we're multiplying x times 2y plus 9. So x times 2y plus 9, you have to distribute that. So I'll write it out like this first, so I can indicate that this x has to be distributed to be 2xy plus 9x equals 18. And since we're solving for y, that means we can subtract 9x from both sides. So 2xy equals 18 minus 9x. We can now divide by 2x. Right? Anything multiplied to y can be divided out, which means not just 2, not just x, but the entire 2x. Which makes y equal to 18 minus 9x over 2. So this is our inverse. H of x was our name of the function. So that means h negative 1 of x equals 18 minus 9x over 2x. This should be a 2x over here. Sorry about that. And then, it looks like there's something that can reduce. Maybe the x's can cancel out. They cannot because of this minus sign. Maybe 18 and 2 are both even numbers. Can you divide that by 2? No, you cannot. Again, because of this minus sign that's outside the parentheses. Reducing this function is a no-go. So leave it like that. Last one is fairly, there's a little bit more involved here, but we're going to start out exactly the same way. First, setting y equal to 10x minus 7 over 4x plus 11. And then swapping, moving forward from here, this red arrow, swapping our x and y values to get x equals, you know what, let me give myself a little more space on top so I'm not, doesn't feel so cramped. That looks better. X is equal to 10y minus 7 over 4y plus 11. Notice that we had two x places here, two x values, which means both of these x values got replaced with a y variable. And now that this is a proportion, once again, we can cross multiply to get x times 4y plus 11 equals 10y minus 7. Distribute the x once again. 4xy plus 11 equals 10y minus 7. Oop, that's 11x, sorry. 4xy plus 11x, because it got distributed. So we want to solve for y, right? We want to solve for y, which means that we should do our basic algebra steps, our equation algebra steps, which means we want to get y by itself, which means we want to move our y variable and everything attached to that y variable over to one side. And that also means that anything that is not attached to a y variable is going to get moved to the opposite side. So subtract 10y from both sides and then subtract 11x from both sides. We'll get 4xy minus 10y equals negative 7 minus 11x. Now comes something a little bit unique, but we have 4xy minus 10y. They are not like terms, so they cannot be added or subtracted. What we can do is on the left side here, we can factor out using a greatest common factor the variable y. We cannot proceed with anything else, right? We can't divide by anything on the entire equation that's gonna make things, work out. So let's factor out our y. So we get y times 4x minus 10, and that's in parentheses. This is equal to negative 7 minus 11x. Now, once again, just off to the side over here, I'll do this in this color pink. If you are solving this equation, 5x equals 15, right? Why are we dividing by 5? We can choose to divide by anything we want to, but we're dividing by 5 because 5 is what's being multiplied to our variable, and it's going to make it cancel out. So by that same token, what we need to do here is divide out by what is being multiplied to our variable, and that is this entire binomial 4x minus 10. So we divide everything by 4x minus 10. That's going to cancel out, divide out to 1 over there, and leave us with y equals negative 7 minus 11x divided by 4x minus 10. And this, in fact, is our inverse. F negative 1 of x is equal to negative 7 minus 11x divided by 4x minus 10. I hope that shed some light on finding inverses algebraically and graphically, and also what the inverse of a function really means. Thank you for watching, and I'll